Welcome back to the Explainer. So I am absolutely thrilled you're here today because we are taking a huge step forward in our machine learning journey. In our previous Explainer, we completely decoded binary classification, training models to make those simple this or that decisions. But today we're pushing past those boundaries. We're going to tackle the complexities of the real world by transitioning from binary classification into the truly fascinating realm of multi-category predictions. We're going to break down the math, look at real numbers, and make multi-class classification completely intuitive for you. Okay, let's dive into this. Here's our roadmap for today. We'll start by recapping binary classification, then introduce the multi-class classification problem. After that, we'll explain the softmax formula, calculate some multi-class probabilities together, and finally, do a side-by-side binary versus multi-class comparison. All right, let's kick things off with part 1, recapping binary classification. Let's briefly anchor ourselves using what you already know about binary models. Think back to our customer churn model, where we predicted if a customer would either cancel or stay. Say our customer's feature vector, their data profile, shows they have 4 monthly usage hours, 3 support tickets, and 1 late payment. Our logistic regression model processes this and calculates a single raw score Z. It does this by multiplying those features by learned weights and adding a bias, which gives us a raw score of 1.9. But 1.9 isn't a probability, right? So we feed it into the sigmoid function to squeeze that raw score down into a usable percentage. And when we run that 1.9 through the sigmoid function, boom, out pops our probability, 0.87. This math definitively tells us the model estimates an 87% chance that this specific customer is going to cancel their subscription. Finally, to make its actual decision, binary classification uses a strict, hard-coded threshold. Because our probability of 0.87 is way higher than the standard 0.5 cutoff, the model confidently predicts class 1, that they'll cancel. It's simple, it's elegant, and it's highly effective when you only have 2 choices. But here's the catch. What happens when there are more than 2 choices? Let's see how this builds, because this beautiful simple binary model, it breaks completely when reality hands us 3, 4, or maybe even 50 different categories. Which brings us to part 2, the multi-classification problem. So how exactly do we teach a machine to choose just one correct class from a whole menu of possible answers? Let's look at a really tangible, real-world example. Imagine you're building an automated system to route customer support tickets. When a customer sends a message saying, "Hey, I can't log into my account," your model can't just reply yes or no. It needs to classify that ticket into one of several distinct categories. Is it a billing issue, a technical issue, an account access problem, or just a general question? This scenario right here absolutely requires a multi-class approach. Now, notice the massive architectural shift this requires. In binary classification, the model computes just one overall raw score, our single Z. But here's the multi-class innovation. Instead of that single score, the model now calculates individual raw scores for every single category. It computes a Z-score for billing, another for technical, another for account access, and so on. It's essentially measuring how strongly it leans toward each specific class, all at the same time. Okay, moving on to part 3, the softmax formula explained. Now, what's really interesting about this next part is the math. Because we're juggling multiple raw scores now, our old friend the sigmoid function just won't cut it anymore. We need a new mathematical hero. Enter the softmax function. Now, don't let the notation intimidate you. It's actually incredibly elegant. To find the probability for any specific class, which we call P sub I, we take the mathematical constant E and raise it to the power of that specific class's raw score, Z sub I. Then, we divide that by the denominator. And what is the denominator? It's literally just the sum of those E to the power of Z values for every single class combined. This brilliant little formula is exactly what converts multiple competing raw scores into clean, usable probabilities. Let's break that intimidating formula down into 3 really beginner-friendly core functions. First, softmax looks at all the class scores together as a group rather than in isolation. Second, it turns each individual raw score into a positive probability. And third, and honestly this is the absolute magic of softmax, it mathematically enforces that all of these probabilities will always add up to exactly 1. All right, part 4, calculating multi-class probabilities. Talk is cheap, so let's look at the definitive proof and calculate some actual numbers to see exactly how softmax operates. Imagine a single support ticket comes in, and our model calculates 3 raw scores for it. Let's say it gives a z-score of 1.2 for billing, 0.7 for a technical issue, and 2.5 for account access. Now remember, these are just raw mathematical scores right now, not percentages. To find our actual probabilities, we plug those raw scores right into our softmax formula. For billing, we calculate e to the power of 1.2. For technical, it's e to the power of 0.7. And for account access, e to the power of 2.5. We then create our denominator, that sum we talked about, by just adding those 3 exponential values together. Finally, we divide each class's exponential value by that total sum. Simple as that. And here are the final calculated results. As you can see, softmax successfully converted those clunky raw scores into beautiful, easy-to-read percentages. Billing becomes 0.19 or 19%, technical issue becomes 0.12 or 12%, and account access becomes 0.69 or 69%. So the absolutely crucial point here, the very best part of softmax is how it mathematically guarantees these probabilities add up perfectly to 1.00. Look at it, 19% plus 12% plus 69% equals exactly 100% of the total probability space. The model has perfectly distributed its certainty across all the available options. Now, how do we make our final prediction from this? Well, contrast this with binary classification. Back in the binary model, we used a strict 0.5 threshold. But in multiclass, our decision rule is beautifully straightforward. We simply pick the maximum probability. Since 0.69 is our highest number, the model confidently predicts account access. There's no need for fixed thresholds here, just pure comparative logic. And that brings us to our final section, Part 5, Binary versus Multiclass Comparison. Let's definitively compare these 2 foundational models side by side, just so you have a crystal clear mental framework of their functional differences. Sigmoid is your go-to tool for 2 classes. It takes exactly 1 raw score and spits out exactly 1 probability. Softmax, on the other hand, is your tool for the wider world. It takes multiple competing raw scores, normalizes them, and outputs a spread of probabilities that cleanly add up to 1. To really summarize our entire journey across these dimensions, if you have exactly 2 target classes, you're doing binary classification, utilizing the sigmoid function and making your final choice using a set threshold, like 0.5. But if you have more than 2 target classes, you've stepped into multi-class classification. You upgrade your math to the softmax function. You calculate probabilities for every single category, and you make your final decision by simply choosing the maximum probability. You've just leveled up from simple binary decisions to mastering the math of multi-class probabilities. You now understand not just the high-level concepts, but the actual formulas and the hard numbers behind how machines make complex choices. So I'll leave you with this. Are you ready to take these frameworks and start building classification models that can actually handle the full, messy complexity of the real world? Thanks so much for joining me on this explainer. Keep studying, and I'll see you next time.